Welcome to the AP PreCalculus video on topic 2.3 exponential functions. I am Coach Meidenbauer, and let's just get at it. This is mostly an Algebra 2 topic, so we will go through this pretty quickly. We will kind of amp it up a bit to show you the PreCalculus portion of the exponentials. But what's important here is just knowing what an exponential function is. As you can see right here is our general form of the exponential function, which is going to be a times b to the x. Okay, the coefficient of b cannot be zero, otherwise it's a zero function. And then b must be larger than zero, but can't be one. Because if b is just one, then it's just a constant function. Okay, so exponential growth. If you want to know if a function is growing, that means that the a value is positive and the b value is larger than one. If the function is decaying, then the a value is positive and the b value is between 0 and 1. And we're going to talk about both of those here in a second. Directions for this says to sketch a graph of each function and show at least 3 key points. We're going to indicate whether these graphs are concave up, concave down, increasing, decreasing, all that fun stuff. Okay, so we're going to first focus on this one right here, this 2 times 3 to the x. So just to remind you how to graph exponential functions, what you're going to do is you're going to pick on 3 main points, x points. So I make a little chart right here. I always use for exponentials -1, 0, and 1. That's what we always use for exponentials. And then if I'm looking at this one right here, the parent function is just 3 to the x before there's any transformations. Okay, so 3 to the -1 gives me 1/3. 3 to the 0 gives me 1. 3 to the 1 gives me 3. Okay, now to sketch this actual function, it's going to be 2 times that. So multiply all these values by 2. Okay, and that's going to give us these points right here. -1, 2/3. We're just estimating that 2/3. 0, 2, and then 1, 6. So the function looks like this. This is nothing new. This is just all recall. And we have a horizontal asymptote here. Okay, so every single exponential function has a horizontal asymptote. We didn't push anything up or down, so it's going to remain at 0. Now, this does mention to talk about if we are increasing, decreasing, concave down, concave up, whatever. This function is an exponential growth. Okay, so we'll define this as a growth because our a value is positive and our b value is larger than 1, which means in this case we are increasing and we are up like a cup. We are concave up. Okay. Same idea over here in terms of graphing it. So I'm going to make an X chart using -1 and 0 and 1. And my parent function here is going to be 1/3 of the x. Now, when I plug in a -1, it just flips it. It gives me a 3. This gives me a 1. This gives me a 1/3. And then for all of these, I'm just going to multiply them by 2. So I'm going to get 6, 2, and 2/3. If you notice here, the x's really just got flipped here from the previous picture. So I'm going to go ahead and sketch this. Okay, and this is going to be a decay because our a value is positive and our b value is between 0 and 1. So, and this is going to be decreasing and concave up. Just look at it, you can tell it's concave up. Okay. Let's go on to some behaviors with this on input and output values. So as long as our x values are of equal length, which they will be for these exponentials, we're not going to do anything too tricky on that. The output values of exponential function are proportional, which means that we can multiply a number by something to get to all of these. So if I'm looking at this example 1, I have 2 different graphs here. So we're trying to figure out what a proportion is. We're given that we have an exponential function, so we know that we need to multiply by a number to get from one to the next. So if we're looking here on the left-hand side, what number do I have to multiply to get from 2/25 to 2/5? Now, if you're lost, like, I don't know that. These are all going to have the same proportion. Find one that's easy. Like, to get from 2 to 10, we should know what we need to multiply for that. That's definitely a times 5. Okay, so the proportion to get from one to the next is going to be a 5. So to get from 2 to 10, multiply by 5. To get from 10 to 50, multiply by 5. So then you can kind of see here, all of these are going to follow suit. So for all of these, multiplied by 5, you'll go from 2/25 to 2/5, multiplying by 5, 2/5 to 2, multiplying by 5, and so on and so forth. This next one, these values are getting smaller. So this is a decay. So our proportion value is going to be between 0 and 1. How do we get from 27 to 9? Might be saying to yourself, we're dividing by 3. I agree you're dividing by 3, which is the same thing as multiplying by 1/3. So our proportion here is going to be 1/3. And you're going to notice that's true for all of these. Okay. We're going to talk about an additive transformation here. So we're going to add in just a little bit of a vertical transformation. So we're given this chart, x values and h values. We don't have f, but it says here to complete this value, to complete this table. And so all we're going to do is solve for f. So if h is f plus 5, then f of x, if you just solve for f, is going to be h of x minus 5. So I can minus 5 all of these. So 7 minus 5 is going to be, what just happened? 7 minus 5 is going to be 2. 9 minus 5 is 4. 13 minus 5 is 8. 21 minus 5 is 16. And 37 minus 5 is 32. Okay? So this is exponential. And how do we know it? Well, because we are proportional by multiplying by 2. So here we're going to write down how we know that exponential, because our output values are proportional. I can't even spell proportional. By 5. Okay. Last thing here, which is going to be newer for us, is just this limit notation. So end behavior of exponential functions. Okay. This is all it's saying. End behavior for exponential functions. You're either going to have the exponential function is going to go to infinity, go to negative infinity, or level out at 0, depending on where the asymptote is. So we're going to use our limit notations to describe all these 4 functions. Okay. So for the first one here, this is an exponential growth, and it's positive. So you can tell that our limit behavior, as we go to negative infinity of this f of x, this is clearly getting closer and closer to 0 on the left-hand side. So that's going to be over here. And then our limit, as x approaches positive infinity of f of x, going right up there for positive infinity, and that is going to equal positive infinity. Now, this is almost the same thing for this next one, but we have a negative a value in front, which is totally fine. As you can kind of see, I'm going to kind of trace this for you so it's a little bit easier to see here on the video. Our left end behavior is still going to 0. So our limit, as x approaches negative infinity of, this is g of x, is equal to 0. And our limit, as we go out to positive infinity of g of x, is going to be negative infinity. This one right here, we have a decay. It's a positive decay. So I'll trace this. Our left hand behavior here, you can tell it's going up. So our left hand behavior, which means we're approaching x negative infinity here of h of x, is going to equal positive infinity. Our right hand behavior is going to level out at 0. And last but not least, we have k here, which is the flipped version of a decay. So our left hand behavior for k of x is going to approach negative infinity, as you can see. And then our right hand behavior levels out at 0. So that's going to equal 0. And that is going to wrap up our video here at Exponentials. We will do a lot more with upcoming lessons. This was just really looking at graphs and analyzing them. Again, I'm Coach Meinbauer, and do not forget to like and subscribe.